Hello, everyone, and thank you for attending today's webinar, Meeting the 5G xHaul Challenge, sponsored by Ericsson, Fujitsu, Juniper, and Viavi. Before we begin, I wanted to cover a few housekeeping items. On the right-hand side of your screen is the Q&A. If you have any questions during the webcast, you can type your question into the Q&A box and submit your questions to our speakers. All questions will be saved, so if we don't get to answer you, we may follow up via email. At the bottom of your audience console are multiple application widgets you can use. If you have any technical difficulties, please click on the yellow Help widget. Here you can find answers to common questions. A copy of today's slide deck is available for download in the green Resource List widget. Towards the end of today's presentation, we'll ask for your feedback. The survey will pop open on your screen and will only take 1 minute to complete. Your feedback is extremely helpful. An on-demand version of the webcast will be available about 1 day after the event and can be accessed using the same audience link that was sent to you earlier today. I would now like to turn the event over to Heavy Reading Sterling Perrin. Sterling?
Thank you, Kelly, and hello. Welcome, everybody, to today's webinar, Meeting the 5G xHaul Challenge, sponsored by Ericsson, Fujitsu, Juniper, and Viavi. You'll see in a minute we've got a full roster of speakers here. So my comments will be brief. Let me just put this webinar in the context of an overall bigger project. So xHaul is the term we use in many for the 5G transport, including Fronthaul, Midhaul, and Backhaul. That's the subject of the webinar, and this is part of a larger multi-sponsored project we have going with this sponsor group, and includes a survey, which we've actually just closed. We got over 100 operator responses to that survey that has closed, and we are in the process of putting together a report, white paper, based on the results, and that'll be distributed free, thanks to our sponsors, to everybody who is attending and registered for this webinar. There's also going to be a set of videos and a couple of blogs all around this very fertile topic of 5G transport. Let me introduce our speakers here, and they'll really carry us through the rest of the next, I would say, 45 minutes or so of presenting, and then at the end we'll open it up for Q&A. But our presenters today will be Amit Bhardwaj. He's Director of Project Management with Juniper Networks. He'll be joined by Hemant Malik. He's Global Head of Product Line 5G Transport with Ericsson. Joe Mascherino, Principal Solutions Architect with Packet Optical Networking within Fujitsu Network Communications. And then also joined by Reza Vaizgami, who is Senior Manager of Product Line Development with Viavi. So they will basically carry us through the remainder of these bullets here as they present, starting with Ericsson giving us a view of how the 5G new radio drives basically is the driving point for the 5G transport evolution. Then moving into Viavi, who will present on transport synchronization requirements, specifically focusing on Fronthaul there. Then Joe Mascherino from Fujitsu will take us through edge transport solutions and the various options, technologies, and architectures for that. And then we'll wrap up with a look at convergence, and we'll bring in Amit from Juniper to carry us through looking at xHaul in the overall context of Metro and Edge. And then, as I said, we'll have time for Q&A. We've actually got a good-sized crowd on this webinar, and we're already getting some questions in, so I think we'll have quite a few, which we definitely welcome. And if all goes according to plan, we'll have plenty of time for those. So with that, let's bring in Hemant to carry us through the first part of the presentation. Hemant, I'll hand off to you right now.
Thank you, Sterling. A very warm welcome to everyone on this webinar. I'm glad to be here presenting in 5G transport. Before I start on the 5G transport, some of the I think data points which are very important to understand. They will impact evolution to 5G as well as on the transport networks which will connect the 5G RAN with the core. I think what we are seeing is, and this I'm referring to Ericsson Mobility Report, what we are seeing is the mobile subscription from 2018 to 2024 will grow at a CAGR of 2%, which is 7.9 billion in 2018 to all the way 8.9 billion in 2024. Similarly, this smartphone subscription that will move from 5 billion in 2018 to 7.2 billion by 2024, which is 6% CAGR. If I talk about the mobile traffic, mobile data traffic, it will grow from 27 exabytes from 2018 to 136 exabytes by 2024, which is a 31% CAGR. And similarly, the data for smartphone traffic will be from 24 exabytes to 128, which is again a 32% CAGR. If we look at what will be the situation of traffic on 5G networks in 2024, so 25% of the global traffic will be carried on 5G by 2024. So now I come on to what is driving the bandwidth for transport networks when we evolve from 3G, 4G to 5G. I think there are essentially RAN features or radio network features which are building up to this bandwidth, and we will talk about what are those and how they impact the overall bandwidth. The first is the new spectrum, the NR spectrum. I think the bandwidth which RAN networks can deliver per UE peak and average throughput is actually dependent on how much the spectrum is available. And what we are seeing is the NR spectrum availability is pretty much high in mid bands up to 150 megahertz and in high bands up to 800 megahertz. So when we talk about this mid bands and high bands, I just want to mention the low bands we say is below 1 gigahertz, mid band is 1 gigahertz to 6 gigahertz, and high band is 24.2 to 86 gigahertz. So it is a directly proportion of the radio spectrum available. Then we talk about coordination services. So some of the coordination services which essentially enables more efficiency on the radio networks as well as help to deliver more bandwidth. So we talk about dual connectivity, where in the UE it connects to multiple radio sites so that the performance is enhanced, the signal performance is enhanced, and it can help achieve more average throughput per UE. Then is the spectrum sharing between 4G and 5G. This enables more bandwidth 5G services of the same spectrum which was available on 4G. So service providers can actually shift spectrum between 4G and 5G and enable more bandwidth. Then is the carrier aggregation. I think this is where in multiple radio spots or carriers they can be aggregated to deliver a thicker pipe. So all these coordination services, they actually increase available spectrum or make the more efficient use of the existing spectrum for high average and peak UE throughputs. Similar comments on radio functionality. I think with evolution towards 5G, we are seeing higher modulation. What it means is carrying more traffic on the same amount of spectrum by increasing the modulation. Another technique is beamforming, which is dedicated radio bandwidth towards a particular UE or set of UE so that it can provide more downlink or uplink bandwidth. Then the last but the most important is massive multi-user MIMO. So what MIMO enables is it enables multiple inputs and multiple outputs for the same set of spectrum so that can be reused to deliver more bandwidth for the same amount of spectrum. So as we see, there are multiple factors all the way from spectrum itself to the efficiency and the more latest technologies to deliver more bandwidth per UE. Similarly, I think I will talk a little bit more on the architectures. I think as we evolve from 4G towards 5G, the radio architectures are evolving as well. We know DRAN, which is actually the flat architecture, wherein the radio and the baseband are at the same site. Then we move from DRAN to CRAN. CRAN architecture, wherein is the baseband is located at a central location. This is predominantly used wherein we need more coordinated services, especially in the higher bands of the spectrum. Then we talk about VRAN. In VRAN, I think the radio functionality or the radio functions and the baseband functions, they all can be split and there are interfaces which are required to connect each other. I'll just talk about those interfaces in a while. And then, of course, ERAN, what it enables is, we call it elastic RAN. What it enables is it enables a CRAN kind of a baseband pooling functionality, having a DRAN architecture wherein the basebands at various DRAN locations, they can be utilized across the location. So coming to these architectures, you see that it's not only the user traffic, but it is the control traffic itself, which is actually required to be transported from one point to another. If we talk about CRAN, I think this is where the CPRI interface comes into picture, and as you can see on the slide, there are strict latency requirements less than 75 microseconds, and I think the bandwidth varies from 10 to 25 G per sector. Similarly, in the vRAN architecture, I think the bandwidth requirement is also 10 to 25 gigabit per sector, and the latency requirements of 75 microseconds. When we talk about ERAN, I think the E5 interface, which connects two node Bs, G node Bs, the bandwidth goes all the way up to 75 gigs and latency requirements of less than 30 microseconds. So 75G is actually 3 into 25G. Over and above, when we see there's a new open ORAN architecture, which can be applied to DRAN, CRAN, or vRAN. All it talks about more open interfaces, and what it talks about is how to connect a heterogeneous kind of a network, having a radio functions as well as a baseband functions separated or from a heterogeneous environment. Now, having all these bandwidths and the performance latency requirements, I think it's a critical question how much the networks are prepared today. So where we see today the networks are on the left-hand side, wherein the per site transport requirements are less than 1.5 Gbps, and the interfaces they connect are gigabit interfaces or multiples of gigabit interfaces. Now, when we evolve from baseline capacity coverage to LT evolution gigabit LT towards 5G, I think this is the inflection point. What happens is the transport capacity required moves from less than 1.5 Gbps to all the way up to 20 Gbps, depending upon the spectrum availability, depending upon the connectivity services or the coordination services configured on the radio networks. Similarly, we see the technology, the backhaul, it can be connected using microwave as well as fiber, and of course the interfaces are, for the fronthaul especially, are CPRI, which is a native TDM, moving all the way to eCPRI, which is more towards Ethernet. And the architecture evolution happening from inflection point is, I think, DRAN, CRAN, ERAN to all the way up DRAN, CRAN, ERAN, vRAN, and ORAN. How to enable all this? I think it's important to understand there are various architectures, and they will evolve over a period of time. The transport networks have to be built once, and what all service providers they need is to build those transport networks today to actually have all these types of DRAN, CRAN, vRAN, and ERAN architecture. There might be cases wherein the operators they evolve from one to another based upon the geography, the services supported, as well as the type of market. So what is essential is that transport network has to behave as a toolbox. It can support any interface, as we have seen the various architectures. It should support any medium, because there will be more number of 5G sites, and of course anywhere, any geography, moving from ultra-dense urbans to all the way to rural and semi-urban, and connecting this bandwidths and interfaces to a common 5G core. So architectures are changing, but the core is remaining common, and transport has to evolve to support all the functionalities, interfaces, mediums, and number of sites. Last but not the least, I think for efficient transport networks, it is important to have an end-to-end automation and orchestration network. So if we have, let's say, radio network connected by fronthaul, backhaul, and core network, it needs to be managed for an efficient slice, common orchestration and management function, so that you can deliver a slice service request, which includes a request of latency, bandwidth, or wavelength, etc., and can reserve resources and withdraw resources all the way from RAN to core through a transport network seamlessly. With that, I think I will request my colleague Reza to take over and talk about more detail in the interfaces and the synchronization requirements. Over to you, Reza.
Thanks, Hemant. Welcome, everybody. I'm here with Viavi Solutions, test and measurement company, and we'll cover the transport and synchronization on Fronthaul part of the network. As you will see, lots of interesting things happening in that part of the network, and we'd like to provide a little bit more details on that. So, but before we get to the new requirements, let's take a look at what we have right now in 4G in terms of Fronthaul. Many of you are familiar with Common Public Radio Interface CPRI, which is the mainstream technology used for Fronthaul. Very simple technology, synchronous technology, really allows us to develop these simple radios, light radios that we all know, remote radio heads, and at the same time allows coordination of sites, which is very important when we get to LTE Advanced and 5G, comp, etc. We have CPRI version 7, which allows us to go up to CPRI rate 10, which is 24 gigabit per second. So good, very simple technology, but of course we wouldn't be talking about it if there was not a challenge with it, which is when we get to 5G. And as we actually already evolve towards 5G, we are seeing more and more bandwidth. Hemant talked about it in previous slides. You know, we are talking about larger number of antennas. The massive MIMO is a big topic. Also larger bandwidth, signal bandwidth, so we could go 100 megahertz and higher. So when we deal with CPRI, CPRI is a very simple technology. It's like TDM in the past, and so it's basically is inefficient, and its bandwidth increases with the number of antennas and signal bandwidth. So I put a simple table together. You see when we get to massive MIMO, 64, and there are actually higher number of antennas, 128, and etc. We get to optical bandwidths which are in excess of 100 gigabit per second. So that becomes a little bit expensive if you are putting this kind of optics on a radio. And that's why we need a new solution when we get to these new bandwidth requirements. How we get to the solution, so to understand why we have this challenge actually with CPRI, we need to know where it's coming from. When you look at baseband unit and a radio, most of the processing actually happens in the baseband unit. We have all these functional elements on the left-hand side. This is down to the PHY functionality, and then the radio functionality is in the remote radio head. That's what makes the CPRI simple, but at the same time very bandwidth inefficient. And so naturally, when we want to talk about a solution, we need to think about whether we need a new functional split where we put maybe some more functionalities into the remote radio head to cut the bandwidth. Lots of discussions have been going on this functional split for the last 4.5 years, but we are going to summarize it and just focus on one application, which is mobility. And so the proposal has been to put some of the PHY functionality into the radio, and by doing that, we can actually significantly reduce the bandwidth and make it more actually variable, so it's not constant like in the previous technology CPRI. It makes much better use of the optical bandwidth and transport network that we have, and at the same time still allows us to do things that are essential for mobility, which is coordination of multiple radios. This is very important for mobility application. That's why this option, which is also known as option 7, is so important for eCPRI. Now, as we get to the transport requirements for eCPRI are very similar to CPRI. So we are talking about a technology which is very latency sensitive. Different numbers are being used in different presentations, but I'm going with what CPRI organization has proposed: 100 microsecond one-way delay between a radio and the distributed unit, or the BBU. And this is primarily for user plane traffic. When we go to CNM control management plane, we got less less stringent requirements, 100 millisecond. 10-7, and again, less stringent with CNN plane here. Of course, when we design networks, we would need to bear in mind the most stringent requirements. That's why most of the focus has been basically on the 100 microsecond, which translates in, if you are taking a fiber line system between a radio, you know the speed of light on fiber, basically we have 5 nanoseconds per meter. So that translates to maximum of 20 kilometers. In reality, of course, you would like to leave some margins, and you are getting somewhere below 20 kilometers. But these are the requirements that have been basically delivered by CPRI organization. So what it means really for our initial 5G deployments, we are seeing a lot of networks that are being designed, and primarily right now with dark fiber, short links between the radio units and the distributed units, which are often located at the bottom of a tower or in a maybe basement of a building. But of course, dark fiber is not quite so efficient. It's okay for initial low volume deployments. When we go to higher deployments, especially in rural areas, in metro areas, we need something more efficient that makes better use of fiber. So WDM is already being tested in the networks. But even WDM, as we know, it's not quite efficient. Still, it's locking bandwidth and locking wavelengths for different radios. And that's why the technology community, the transport vendors, everybody is looking at enhancements for PON. We need new PON technologies for Fronthaul that deliver better delay performance on the uplink. Lots of good work is going on by PON equipment manufacturers and other participants of the ecosystem. And finally, TSN. And TSN is the timing-sensitive network, which is Ethernet-based technology. And basically, it was driven, among others, by IEEE 821 working group, which deals with and it defines the requirements for the basically timing-sensitive networks that can carry fronthaul traffic without breaking the radio traffic. And so basically, it defines two categories for CPRI traffic, which looks very much like what we had in the CPRI organization, and for eCPRI. Again, very similar. It has more categories for mobility, 4G and 5G and R traffic. It says 100 microsecond, but it has also even more stringent class for ultra low latency, down to 25 microsecond. So we have these requirements from the IEEE, and you see lots of that overlaps with what we see from CPRI and other organizations and manufacturers. And finally, what I would like to cover is the synchronization. Of course, as we get to 5G, we are dealing with a lot more radios. Many of them will be indoors, in metropolitan areas with limited access to GPS and or visibility to GPS satellites or GNSS satellites. So it's very important to provide a network-based synchronization, something like PTP and synchronous Ethernet. And that's why it's very important to bear in mind what are the requirements. The requirements for synchronization, really, as in the past with 4G, coming from the 3GPP requirements, and those are usually defined in terms of time alignment error, TAE. If we translate that into our transport networks, they translate into what's known as time error, which is basically the difference between the time you have at the reference point in the network and your reference timing source, which would be GPS, GNSS satellites. So those are defined, and for them there are different categories. The categories are determined by what the 3GPP applications require. So when we look at the diagram on the right-hand side, there are different use cases. The lowest, what is currently also known as category C. Category C is what we have also in 4G backhaul networks. and it translates into a synchronization requirement of 1.1 microsecond time error. So at any point of the network, you may not have more than 1.1 microsecond difference to the GPS satellite reference, right? That's the least demanding. When we get to more demanding applications like interband carrier aggregation, intraband, non-contiguous carrier aggregation, etc., we get into a category which is known as category B. For that one, you see we have synchronization requirement which is like 100 to 200 nanoseconds, so much more demanding. And then you got the category A, that's interband contiguous carrier aggregation, that's category A. And finally, when we get to applications which require MIMO and transmit diversity, this is the one that is the most demanding. And then we get into the 20 to 32 nanosecond range. The reason we have this a little bit of range in time error requirements, it's the following. Because dependent on application and the implementation of the timing functions, for example, where we place the timing, the telecom slave clock, your margins and your limits change. But you see roughly the requirements and the range, and it's much more stringent when we get into these 5G advanced requirements and advanced applications for timing synchronization requirements. So with that, I would like to conclude my part and hand it off to my esteemed colleague, Joe Masserino from Fujitsu.
Thank you, Raza. This is Joe Masserino from Fujitsu, and during this portion of the webinar, I would present advanced Ethernet fronthaul capabilities and network slicing implementation using cloud control plane with MPLS segment routing. Here's an example of an Ethernet fronthaul-based deployment using time-sensitive networking, or TSN, for 4G, 5G, and Ethernet services. The illustration depicts a CRAN architecture of central hub location to multiple cell sites in a point-to-multipoint configuration. The central location is established as a boundary clock, passing timing and synchronization information to the remote cell sites using the time-sensitive networking capabilities. 4G CPRI service channels are encapsulated over Ethernet as radio over Ethernet transport. 5G eCPRI is already in an Ethernet frame format for the TSN aggregator and transport platform. And Ethernet, enterprise data access is passed as Ethernet traffic with preemption, minimizing latency variation on the higher priority traffic, that being timing and sync, 4G and 5G services. Remote visibility and performance monitoring is achieved using standard OEM techniques within the Ethernet protocol technique. The ORAN Alliance is driving openness and intelligence in the radio access network. An area of openness is the physical layer 1 low-order processing stack, otherwise known as Lo-Fi functional split 7.2x. This is moving from the BBU in the 4G configuration to the 5G RU. In moving this processing function from the hub location to the cell site, the protocol is eCPRI, which is an Ethernet form of CPRI that is much more efficient. Applying this concept to the 4G LTE network, as shown here, at the cell site with Lo-Fi functionality will reduce the CPRI rate over the fronthaul up to 5 times. CPRI is extremely inefficient, and eCPRI is much more efficient as a result of this reduction in bandwidth. This means, for example, a CPRI 7 10 gigabit per second service channel would be translated to eCPRI operating as low as 2 gigabits per second over the fronthaul span. Implementation of Lo-Fi to the 4G remote radio head will require the radio vendor to open up the format of their IQ data within the CPRI frame. Once the CPRI is translated to eCPRI, the service channel connects directly to the 5G virtualized OpenDU at the hub location, collapsing the two networks into one. Finally, this openness and remotely deployed technology, the service provider will have the flexibility of multi-vendor interoperation. The illustration shown here, very similar to that first slide that I showed, is again a transport network using time-sensitive networking, aggregation and transport for 4G, 5G, and Ethernet services. However, at the cell sites, we have an additional function using ORAN Alliance Lo-Fi functional split 7.2x. The Lo-Fi functionality is integrated into the TSN aggregation and transport platform, operating as a gateway for 4G traffic to 5G distribution units. Implementing the Lo-Fi functional split into the TSN platform at the cell site will translate the CPRI service channels to eCPRI, which is a much more efficient Ethernet form, reducing capacity by as much as 5 to 1 over the fronthaul network. The Lo-Fi implementation will require the 4G radio vendor to provide openness of their IQ format within the CPRI frame. The low-order PHY translation of CPRI to eCPRI integrates the 4G network into the 5G network at the hub site through the use of the ORAN Alliance compliance OpenDU. This DU is essentially virtualized as a distribution unit. This integrates the 4G and 5G networks, eliminating the overlay, and offers multi-vendor interoperability from cell site to central location. Let's look at the Midhaul and Backhaul sections of the edge transport network here. The Midhaul and Backhaul segments of the network will also undergo a major change. With the multiple use cases envisioned for 5G traffic, the point-to-point and point-to-multipoint network will evolve to an SDN mesh network with virtualization. Traditional routers will be challenged since they are comprised of an integrated control and user plane. They may have several chassis to support different capacity versus cost requirements, but the chassis limits will dictate their scalability limit. This is referred to as a scaling up or scaling up to a limit, as defined by the chassis and integrated control and user plane capacity. And an initial network deployment using a traditional router will consist of control and user modules in a chassis that is 20 to 30% utilized, but the operator will have to allocate the max footprint, power, and thermal reserve. Then there is the performance capacity risk of over or under engineering each site. Deploy a platform too small and not meet demands, or over-engineer the site, resulting in inefficient CapEx use. Essentially, an integrated control and user plane router platform scales up to a limit, which results in inefficiencies and potential lost revenue opportunities. Network slicing as a service will require the network elements to operate with virtualized network functionality. The disaggregated router shown here has its control plane in the cloud and MPLS segment routing user plane in a high-performance programmable platform. As the network slices are defined in the network, virtual router instances are configured in the cloud, as shown here. Over 100 virtual router instances can be configured for each network element. The cloud control plane will automate and provision metrics using zero-touch provisioning, then push the programming down to the user plane infrastructure. Here I'm showing one network site, but imagine many of these sites configured in a mesh topology, all simplified using this cloud control plane approach. This disaggregated cloud control plane approach offers the ability to scale out, providing multiple virtual router instances per network element, and automation interconnecting all the services with required SLAs. So finally, on my last slide, I'm showing a network slicing as a service application. This will require elements to operate with virtual network functionality. The disaggregated router shown here has its control plane in the cloud and MPLS segment routing in the user plane in a high-performance programmable platform. As the network slices are defined in the network, virtual routing instances are configured in the cloud. As over 100 of these network routing instances can be deployed in this fashion. As customers' VPN are provisioned within the network slices, full resource guarantees and isolation in both the data plane and control plane are administered. Operational costs and complexity is greatly reduced by creating and dynamically managing discrete virtualized networks over a common infrastructure along with automation. The result is one common infrastructure with multiple virtual networks. So let me hand off our next section to my colleague, Amit. Amit?
Amit, are you on mute?
Sorry. Thanks a lot, Sterling. I was in mute.
Okay,
thanks. So thanks, Joe and Sterling. So I'll talk about the Metro Fabric in terms of taking all the access and aggregation use cases on a converged infrastructure to provide the lowest TCO. So let's look at what's changing when we look at the Metro networks, right? So today, the Metro networks, all the traffic is taken from the access, basically mobile, business, or residential to the edge, and all the services are provided at the edge of the network, right? And as we move from TDM to IP, the networks really did not change that much in the sense that all the network basically services are provided at the edge of the network, right? And as we move towards the next generation networks, the few things that are changing. One, the content is basically getting hosted in the Metro. And as the content is hosted in the Metro, which is driven by the video applications, and the second, the cloud's customers basically are moving their presence as close as possible to the end customer, which is basically hosting all the peering applications, for example, from one stop from the edge customers, from the end customers. And last but not the least, as low latency applications start to be driven from the metro networks, then more and more content starts to move into the metro networks. So when we look overall, from a network perspective, you're looking at the flows, where in the past, the flows were all static, point to point, and now the flows are becoming more diverse in the sense that the flow from the access to the metro, the flows between the applications in the metro, and the flow from the applications in the metro to the edge or in the centralized cloud. So with that, let's look at some of the decision criteria as we look at the fixed and mobile converged networks. What are the areas where the customers will have to make decisions, and what during those decisions, and what are the different technologies that play a part? So as we look at the three key use cases here, one is around the business, residential, and mobile. The businesses are connecting to the cloud as the applications are hosted in cloud. There is also a trend to SD-WAN for business services. Residential speeds and feeds are also continuing to grow with NG-PON and NG-PON technologies. Cable is also going through a complete refresh with virtualization of CMTS and the fiber deep architectures, in effect basically creating a new metro network in the middle. 5G is also trending now currently to the ERAN architectures, which basically what we're looking at in the effect is holding all the common needs. We trend towards cloudification, and this is a time for converging these into a common infrastructure. As we take that to the edge, the question now is, how do we consolidate the edge? And this is where the node and network slicing starts to come into the play. And looking at the lower layer from the fixed mobile convergence, there are clear trends from an optical perspective. And with these clear inflection points, DWDM is becoming a pluggable. And with this pluggable becoming into the routers, we can save tons of space, which honestly can be used for hosting the distributed cloud. And as we look at convergence of this infrastructure, both in the metro and the edge, and even converging some of the lower layers into common infrastructure, the network operations itself become much more simpler because we have fewer elements in the network. So with that, I'm going to talk about basically three key pieces, which is the fixed mobile convergence, cloudification, and the edge consolidation in the rest of the presentation. From a fixed mobile convergence perspective, what's changing is that the speeds and feeds are growing to 10 gig, 25 gig on the axis, and then the metro basically gets upgraded to 100 gig rings and beyond. We're also looking at the new optimal form factors with basically standard optical interfaces that can be integrated into those form factors, driving a common infrastructure for both fixed and mobile. And as part of this, the multiple user planes, basically we're driving multiple user planes with different applications onto a cloud infrastructure, which could be distributed, or this cloud infrastructure is basically centralized from a telco cloud perspective, driving low latency services or high bandwidth services. And then as we look at the cloudification, there are two key protocols that will play a big part. One is EVPN, and other one is segment routing. And the key reasons here basically are that as we look at these protocols, technologies, one is the trend towards simplification. Because on its own, EVPN, for example, you don't need any data plane learning. You can support active-active configurations. You need fewer protocols, for example, with segment routing, and these technologies support both IPv4 and IPv6. But the bigger value of these technologies is because these technologies provide a ubiquitous metro fabric where you can have common overlay, for example, with EVPN, and common transport technologies in the metro as well as in the distributed cloud, in effect providing a ubiquitous fabric in the metro for the applications to move around as well as for connectivity. And then last but not the least is about programmability, where these technologies will have the basic programmable infrastructure to apply the policy on the network. So now let's look at the last piece here, which is basically around consolidating the edge. And here we expect multiple user planes driving mobile, IoT, business or residential. And the ability to basically have the separate control planes for each of these user planes is what allows not only for different variant domains, but also the ability to scale and maintain independently. And this is basically a concept that you take from the data center environment, basically saying that control plane is a workload which can be expanded to different instances for different user planes in the network. In summary, what we're looking at here is there are lots of opportunities, basically, with convergence for doing more with less, simplifying architectures, and in fact, really simplifying operations by reducing both OpEx and CapEx, because we're driving towards more convergence and less pieces in the network, but really doing more with the same infrastructure across business, residential, and mobile use cases. So that's my end of the presentation, and I will pass it on to Sterling for the Q&A.
Great. Thank you, Amit, and thanks to all our presenters. Actually, great job, guys. You're right on time. So let's move into the Q&A right now. And actually want to thank the audience as well, because you've put forward a ton of questions. So let's just jump right into it. The first one, maybe Heyman, I'll start with you on this one. It's a little bit lengthy. Let me just kind of read it through. About eCPRI for RAN on total cost of ownership, saying that the importance of eCPRI on RAN TCO is overestimated. Essentially, developments in silicon photonics are bringing down costs, and a statement it makes an intention to reduce transport requirements at the radio equipment expense, not efficient. And the question is, can you please elaborate on the impact of eCPRI on RAN TCO? So, Heyman, if you can start that, and if anyone else has a comment, they're welcome as well.
Yeah, I think it's important to understand. Again, I will go to the architectural piece of it. It is important to understand what are the main requirements of the Fronthaul network, right? The majority of the concerns are the bandwidth as well as the latency. And when we talk about that, of course, there are multiple ways to achieve it. The two interfaces that we are currently talking is CPRI and eCPRI, right? And to transport both of the interfaces, from a RAN perspective, I don't think there is any restriction, right? From a RAN perspective, they only need, it can be as simple as a fiber connectivity between two endpoints. So there is an option of using a WDM based Fronthaul network for transporting CPRI or eCPRI, as well as multiplexing, lower level of CPRI interfaces into a 10 gig interface. To optimize the fiber infrastructure. So the TCO question is basically how you optimize the fiber infrastructure, how you reduce the requirement of fiber pairs or a single fiber based upon what optical you use, and how many services you can integrate into a single fiber pair. So that is the question. And I think if we compare the technology available today with the WDM passive or active technology, I think the best possible TCOs are achieved today. However, going forward with eCPRI and advancements towards ORAN, I think Ethernet will become technology of the choice as well. Herein again, the competition between the WDM active passive versus Ethernet, I think it has to be seen how many interfaces, what is the density. But I think with the Ethernet switching functionality being made available with eCPRI, I think the TCOs will be further reduced. So that is an overall comment. If anybody wants to add.
Does anyone?
I'd like to also add a piece to that.
Sure.
Sterling. So this is Joe. eCPRI for RAN TCO is also important in that eCPRI is a much more efficient protocol as compared to the 4G LTE CPRI protocol. In fact, one of the points that I went through in my slides with the ORAN Alliance, pulling the low order processing physical layer 1 capability out of the BBU and placing it into the 5G RU is one of the reasons why 5G eCPRI is more efficient. Applying that same concept to 4G technology by placing that functionality in a transport platform at the cell site will take that CPRI and convert it to eCPRI using that low order PHY processor, which will essentially reduce the capacity at which that CPRI channel is passing over the fronthaul as high as 5 to 1. So that's a key area in terms of lending to the total cost of ownership for lowering the cost of optics and maximizing on your infrastructure CapEx to pass traffic over the fronthaul.
Okay, excellent. Let's keep jumping through because again we have quite a few questions. I want to go to the next one. You mentioned ORAN a bit. There is a question on ORAN. Maybe start with Reza on this one, and then again if anyone wants to add. But it has to do with requirements and latency, which Reza you spent some time on. The question is regarding ORAN. What are the latency and bandwidth requirements? Can you elaborate on that?
Yeah. Okay. So thank you. ORAN, basically there are two aspects, right? When we talk about transport requirement, the transport requirement for ORAN should be the same as it is with what we talked about with eCPRI or prior to ORAN, where we didn't have open protocols. So should be the same thing. Now, if you are looking at it from the ORAN Alliance perspective, that they are looking at it from the radio, I call it radio, RAN perspective, and those are the people who deal with the application. They talk about transmit windows and receive windows, make sure that we don't miss packets. So they talk about it in a different way in the ORAN documentations, but in terms of the transport, what it means for me as a transport engineer, it's the same. It should be the same requirement as we had with prior to ORAN with eCPRI.
Okay, excellent. Anybody else want to add? No? All right, let's, maybe Amit, bring you in. There's an interesting question from an operator. It has to do with network slicing, and the comment, it's basically a comment that's a question. You don't need segment routing to support network slicing. As a routing company, you could probably comment pretty well on where network slicing applies and doesn't. I mean, where segment routing
I think, sure. I think these are two separate concepts, segment routing and network slicing. So when we talk about network slicing, in this case, it's about separating each user plane there and managing each user plane separately with having a separate control plane instance for each of those user planes. Segment routing is orthogonal to that, how you would implement the transport aspect of that in the network. So the answer, I think the point is valid, but from a network perspective, these two are orthogonal things in terms of the solution domain.
Oh, you broke up a little bit on the last sentence. You said it's valid, but can you just repeat that?
Yes, so the concept is valid, but these are orthogonal in terms of the technologies in the solution domain, because one is focused more on the transport aspect, and the slicing, I think when we talk about separating the control plane, that's saying that how do we take each of these user planes could be implemented with different technologies, including segment routing for that matter, and separately managing each of those user planes with a different control plane instance.
Okay, excellent. We got a couple questions. So we talk a lot about fiber. I'm primarily a fiber person in my coverage, but we do get questions about microwave and the role in 5G. We had probably two questions on that, which can be basically summarized in what is the applicability of microwave when we talk about all these traffic requirements for 5G, and maybe Fronthaul, Midhaul, Backhaul, where in those would it apply? And I'd open that up to anybody who would want to comment on that one.
Yeah, and this is Hemant. I would like to comment. I think the first statement is microwave is pretty much relevant technology when we look at the 5G transport networks, and I think few reasons behind it. First is the latency. We talked about the latency requirements, stringent latency requirements in the 5G network, and I think when we compare microwave networks with the fiber networks, you'll be surprised to know that the latency in microwave networks is 20% less over the same distance as compared to fiber network because of the different media which it operates upon. Second is, I think there are huge advancements on the microwave technology itself in terms of delivering more bandwidth required for the 5G networks. If I give you current examples, I think we have already demonstrated more than 100 Gbps per link over a distance of little less than 2 kilometers. So 100 Gbps is a capacity which is already being demonstrated. And if we talk about E-band as a technology for delivering a millimeter or microwave, it's capable of delivering up to 20 Gbps per link. Now, if we take into consideration all these pictures and we actually put it on the geographical spread, we anticipate 65% of the end radio sites globally will be on microwave by 2023. If we take out the North Asian market, which is China and Japan, if we include the North Asian market, then the overall fiber to microwave or millimeter wave ratio would be around 40% of being microwave. And if we split out the E-band specifically, it will be 20% of the overall site. So I think, yes, microwave is a very relevant technology for delivering 5G transport, especially in conditions where it is a high band spectrum and we need many more number of sites to provide coverage and capacity. It can provide a fronthaul, it can provide backhaul, and it can provide aggregation services.
All right, excellent. We probably get time for maybe 2 more questions, so let me just keep moving. For the audience, though, there should be a survey up in front of you. If you can just take a moment to fill that out, we'd definitely be very interested in your feedback on the webinar and different topics. Next question, Joe, another operator question came in. I believe it related to your question, and it is there any ring topology possibilities with the TSN, the time-sensitive networking aggregator? I think that's a you question, but if not, somebody else can take it. Yeah.
Sure, I could take that. Well, that time-sensitive networking aggregator and transport platform supports 3 types of traffic, 4G CPRI, 5G eCPRI, and then Ethernet traffic. Ethernet as in business backhaul, Ethernet services, Wi-Fi, basic Ethernet layer 2 type of services. For the Ethernet services, yes, ring topology is supported, but for 4G and 5G, which are extremely latency-sensitive technologies, it is not. So that there are Ethernet fronthaul platforms that support ring technology using G.8031 and G.8032 type of functionality, but that is only valid for the Ethernet transport services. The 4G CPRI and 5G CPRI being so latency sensitive can only go over point-to-point networks, point-to-point, point-to-multipoint type of topologies.
All right. Thank you. And yeah, let's try to find a good one to close out on. Maybe just kind of an oddball question. Yeah, because we did just talk about microwave. We talk about fiber a lot. We just heard about applicability of microwave. There is a question on the cable side about DOCSIS in fronthaul, midhaul, backhaul. I know we're not specific to this in the webinar, but in your discussions and from what you know, and this is for anybody, is DOCSIS even a viable option for transport, given the requirements we talk about?
Yeah, I can take that one, Sterling. Yep. I can take that one. So
Okay.
I think it's really key. In the cable space, currently, there's a big change happening where the cable architectures are changing towards the remote PHY, or remote MAC-PHY, or what everybody calls that cable DAA architecture. And as part of that, everything in the middle is basically becoming a Metro Ethernet network, and the CMTS itself starts to get virtualized. So that Metro Ethernet network is what, with what I mentioned in one of my slides, is basically could be the fixed mobile converged network that drives the backhaul, not just for the cable traffic, right, the residential traffic, but also for the mobile traffic in that scenario. So, in effect, basically, all these technologies are sort of converging together from an architectural standpoint, but also from a backhaul standpoint, and basically seeding the way towards truly a converged network. So, a very valid question, I think. But in terms of what the trends are evolving towards, it's definitely evolving towards a more of a converged infrastructure.
All right, and with that, we're a little bit past the hour, so we'll have to close out here. I know our sponsors for the questions we didn't get to. I know they'll be happy to follow up individually, so look for that. And as I mentioned, there will be a report based on the survey, which I think will also provide additional detail on some of these questions that have come in and some of the topics we've covered. With that, I want to thank our presenters for their excellent presentations in coordination on working on this webinar and project, and also thank you, the audience, for tuning in and for your great questions. Thanks, everybody.
Thank you.
Thank you.